Well, hello everyone. We'll go ahead and get started. Let me go ahead and open them in prayer, and I'll give you a sense of what we're going to be covering today. So, dear Heavenly Father, Lord, thank you for the chance to be working with each of the students in this course. I pray, as always, that the material will be clear. Pray that it can be an enjoyable experience, and it's going to be helping each student as they progress towards getting their degree, and that they can get the job or open the company of their choice as they're finishing up at APU. I also pray that you would help them in their spiritual formation, Lord, that you would help them to really cherish the time they get to study scripture, to enjoy our times that we have in chapel, and help them to be able to draw the theological concepts that we want and how we organize our lives and how to be considering how to bring scripture into every part of our life as we go forward. Also, give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, a couple of things. I sent out an announcement just shortly before class, and so you all can read through that. But the intent of what I'm trying to convey is it's a really important imperative at APU that we create community, that we're able to communicate. And I want to really cherish that time that we have together. So face to face on Tuesdays and via um, Zoom on Thursdays, that I can be here and getting a chance to not only giving a lecture, but also giving a chance that we can have some conversation. And so one of the ways we can be doing that is related to our project work, but also there could be some concepts that are related to the things that we're getting into that I'd like to get your perspective and make sure that you're following along and understanding what we're doing. And so I'll come back to that in a little bit. But for today, we're getting into this next section, which is portions of this are coupled to our first sub-project when we did our digital logic development. And so the ones that we're going to cover first is the number systems. And so remember, we're used to having everything in base 10, but computers are everything is base 2 or multiples of that. And so we want to begin to think from the perspective of what a computer does. And so we're going to look at this in a couple of different ways. And so the decimal system is what we're familiar with. It's kind of by nature, we're familiar with that. And so, but a general way of thinking about this is something called a positional number system. So you could be doing this with base 2, base 8, base 16, or hexadecimal, which we'll explain what that is in this lecture. But ultimately, it boils down to the binary system is sort of the progenitor, if you will, of all of those things on base 2, base 8, base 16. We want to think of how we can be converting between these systems and how we deal with integers, and then how we think of fractions. This chapter gives us a little bit of an introduction to that. I think that will be helpful. And finally, we'll finish up with hexadecimal notation. I wanted to spend more time going over our Mars emulator, so I'm going to have a different program that I'll be showcasing with you. And also flash up I was able to put together what I think is a representation for all of your project ideas. And that's one of the things that we can start to be leveraging as a way of having a conversation about the material we're covering and related to those. So let's go ahead and cover this chapter. And so first of all, the decimal system. And so the digits go from 0 to 9, as we're quite familiar with. And we can be thinking of this construct for 83. We know what this is, but if we were to break it up, it's 8 times 10 plus 3 is actually what it is. And if we have 4, 7, 2, 8, we have 4 of these different things that we have that we're looking at. We say that a decimal system is to have a base or radix of 10. And so we can see how we can quickly go from one to the other. And so that's a general way of looking at numbers that we're familiar with. And if we go to a decimal fraction, it goes the other way. 10 to the minus 1, 10 to the 0 would be the first digit here. So we could write this 3 times 10 to the 0, and then 10 to the 1, 10 to the 2, 10 to the 3. And then for a fraction, it goes in the opposite direction, -1, -2, -3. So the most significant digit is the leftmost digit, and the least significant is the rightmost digit. And so that's going to be if it's an integer or if it's a decimal, that's would be the same. So we can see that we could take some general number here. And so this contains a fraction, a decimal, and an integer portion. And we can see that this number, we could be thinking of this, and the positions where it would be. Position 0 would be where we would have 2 times 10 to the 0 or 1. So we don't need to necessarily show that. So that's a general way of thinking of a decimal number. But we could generalize this. We don't have to do it base 10. We could do it base 8, base 2, base 16. And so now we're getting a chance to see what that would look like with this chart. So here we see base 7. And so we have 0 through 7, or octal would be a way that we can be thinking of this. And so this is not as intuitive for us to be thinking about. So we have to have 4 times 10 to the 7th. And so we figure that out. 3 times 10 to the 3, 2 times 10 to the 2, 1 times 7 to the 1st, 0 times for 10 to the 7. And so -1 is 1/7. And so these are the things that we would be putting together as we go with that. So this is just giving the position. And so if we have, anyway, so we're getting a chance to get familiar with this other way of looking at a different system as compared to what we would have for decimal. So the binary system is now, instead of having a 10, we have 2. And so that's we can start to think of how we're going to convert from one number system to another. And so here would be how we would be looking at that. So if we have this kind of a representation of a number, so we can see these values that we aggregate together. I'll have a lookup table that may make it a little bit easier, but this is going through more details of how formally how all of this works. So converting between binary and decimal. So if you remember what this multiplier is for each digit, it's going to make it a lot easier for you to be doing that translation. There's also something, a binary coded decimal. We'll get into that a little bit later, but just keep that in mind for now. So this is just getting into more details of how we would be figuring out what those numbers are. You can look over this in the textbook, but I'm going to be focusing more on some tabular charts. I think it'll be a little bit easier for you to get a chance to see what this is. So, well, now we want to be thinking, well, how we actually do this conversion from one base to another. And another thing we want to be thinking is how we do addition, subtraction, multiplication, and division. We'll be coming back to that, but this just gives you some ideas of how we could be doing it in a more formal way as you start to take the most significant digit. And so then you would have 5, then you have the remainder that you would be going to the next one, and then you can start to be coming up with this number. So this is indicative of an algorithm that we could be using for putting this into a computer, which ultimately is one of the things that we want to be thinking about as we move forward. So we have the number 10, 11 base 10, and we want to be looking at how to convert that to decimal. And so if we look at this, this is the most significant digit. So this actually represents 8. This represents 4, 2, and 1. You can see you'll start to get familiar with this. So 8 plus 2 plus 1 is equal to 11 is a way of thinking about how to do that. So for 21, so we can see how this one, so this is 1, 2, 4, 8, 16. So 16 plus 4 is 20 plus 1 is 21. And so that just gives you a way of starting to think about it, or you could be doing this this division the way that they're doing it here. Fractions is just going in the other direction. And so we have a table here. So we want to be looking at here as a fraction here. And so we wanted to be having a relationship for this. And so this is would be 2 to the -1, 2 to the -2, -3, -4, -5, -6. And we can see that we can go from this number to this number using now instead of division, we're doing this product. And we're finding out what that number would be. So 1, 1, 0, 0, 1, 1, that's the number that we have there. For this other one, we can see we keep taking that number divided by 2, just take the integer portion, we go down to the next level, and so we can be looking at the remainder. The remainder was 1. So here the remainder is 1. There is no remainder, and then there's 1, and so we can be seeing how that could be working with that. So hexadecimal notation is one of the very common bases that we utilize, and there's actually 16 digits. And so for decimal, we only have 10. And so when we get into the situation, we have to come up with, well, what is a 10? Well, we called it an A, and we go, so 1, 0 to 9, and then A, B, C, D, E, F is the way how we would look at it. And so everything is in base 16 here. So this is how we can be looking at that. So thus, if we can easily go back and forth from one base to another. This is a table that I think is quite helpful, and just starting to get familiar with these relationships are something that would be of use. And so here you can see, like here, 11. So you can think of this, so it's 8 plus 2 plus 1 is 11, and this is where we get the hexadecimal number for that. And so usually what you'll see, the numbers will be grouped in 4, and so that's like a group of numbers that's easy for us to get our head around, and each one of these represent a hexadecimal number. And so you can see this would be 1, that would be 0, this would be 2, so this is going to be all of them together, that's going to be F, and you'll start to see ways that you can go from one to another fairly easily. So it's not, the hexadecimal notation is not only used for representing integers, but also as a concise notation for representing any sequence of binary digits. So guess what? It takes a lot less space than if we had a binary representation or even a digital representation. So that's would be a reason why it's helpful. So why do we want to use it? It's more compact. In most computers, binary data occupies some multiple of 4 bits, and hence some multiple of a single hexadecimal digit. Is an extremely easy to convert between binary and hexadecimal notation. So this just comes back to this. You can see that there's a 1-to-1 translation from binary to hexadecimal. And if we just do this grouping of 4 numbers, we're going to find that's going to be fairly easy. So this was a fairly quick synopsis of doing this numbering systems. And so the key takeaways I just want to have you think about is we think in the decimal system, computers think in a binary system, and one of the ways of aggregating that together is the hexadecimal system, as we saw in this summary table. So there's algorithms to go from the decimal to binary or hexadecimal using going from either integers or fractions. And that's spelled out in detail with what we have in our textbook. So I'm going to pause here for a minute and go back to this chart and see if people are getting the big picture of what we're trying to introduce with this chapter. You can give me a thumbs up or go off mute and give me some of your thoughts. Does this make sense?
I actually had a question on one of the figures that you showed, like from converting decimal notation to binary notation for integers.
Yeah.
I was just a little confused still about like how the process worked for it. Like how does it work like to get like the binary notation? Because I see like when you do 11 divided by 12, it gets 5, but how does the remainder like become 1? Is it because like of the point 0.5 that's greater than 0? Like how does that work?
Okay. Let me spend a little bit of time going over this. So we have, see if I can get, so we're trying to convert 11 into a binary number. And so this is 1 times 10 to the 1 times 1 times 10 to the 0. That makes sense? So, so what we have when we're doing things in binary is we have this quantization based on these digits. And so 1, 2, 4, 8, 16, 32, 64, 128. It's a, you multiply it by 2 to get to the next significant digit. And so 11 divided by 2 is 5, right?
Yeah.
And what's the remainder?
Zero point 0.5.
Yeah. Or you could say if that takes 10, there's 1 left. And so this is the 1 that you see here. So you're either going to have a remainder of 1 or nothing. Okay, we have 5 there. When we divide that by 2, the quotient is 2 and the remainder is 1. So we see that digit, those two are the same. Now 2 divided by 2, the quotient is 1, the remainder is 0. So it divides equally. And then the quotient is 1, and 1 divided by 2 is 0, but there was a remainder, there's a remainder of 1. So that's how we go through that. Does that, are you following what I did?
So you're saying like if we get a remainder in from the result, that counts as 1, but if we don't, that's or if it's just a whole number, then that's 0.
So the quotient of this is how many times does 11 divide by 2? And the answer is 5. Plus there's something left over. 5 times 2 is 10, so the remainder is 1. Okay. Then we take that 5 down here. So how many times does 5 divide by 2? 2 times 2 is 4. So it actually divides by 2, and there's a remainder of 1. So it would be 4 plus 1 would make that 5. Does that help? You seen how that's working?
Wait, could you repeat that 5 over 2 again?
So 5 divided by 2, like what you were saying, is like this would be 2.5.
Yeah.
Well, we're actually not doing it in decimal. we're just doing division. And so long division, so 5 divided by 2 is 2, and the remainder is 1. So this is like you have to think about earlier how you did like long division. And then I'm just going to very briefly show you what that would look like.
All of that. Okay, yeah.
This is what we're doing.
Mm-hmm.
So that just gives you a sense of what's coming. So this is the kind of algorithm that we're using to do that conversion. This is the kind of stuff that you could put it into code and would be very easy to have an implementation of that. Does that help, Nathan?
Oh, because if I reach 2, that's 4. That's 5 minus 4. That's 1. That's okay. Ah, I think I see it now.
Okay, good. I know it's a little bit tricky. Um, so let me see if I can get rid of this here. Um, um, any other comments or questions that people have? This is a basic concept, but it's actually a quite important basic concept. And so what I would have you to leave with you is to be thinking about this kind of a relationship. And when I open up the Mars MIP emulator, you're going to be seeing some examples. I can be showing you with numbers in decimal, binary, or hexadecimal. And so this might be giving you a sense of things that are going to be useful for us. When we get into looking at instruction sets, we're going to see how changing a single bit is going to be important. And that's just a precursor for us to be thinking about that. Does that help out? Everybody else, are you tracking with what we did there? Okay, good. So it's nice to have a straightforward chapter for us to be looking at. Um, so how is it going with everyone doing their digital logic assignment? We're getting pretty close when it's due. Let me double check the due date on that. Um, okay, so it was due last Thursday. And so let me just, if you just want to be doing a thumbs up with the material that we covered in class and what you did with your assignment, was that making sense for you guys? You guys, were you getting a better sense of how you were actually able to program hardware? Maybe for some of you, that was a first experience. Okay, good. Um, Depending on how much time, I can also have folks share um, how it was going for you with your digital logic design. And so I would be happy to do that. And we can also spend a little time next Thursday as well. But let me go ahead and continue to be thinking about some other things that we just had a beginning to have an introduction to the assembly language programming. So the next couple lectures, we'll be finishing up giving some perspective of digital logic, which is related to our project, sub-project 1. And then we get into instruction sets. This is what's going to be strongly related to what we're doing with the Mars MIPS emulator. But one other thing that I captured was I was trying to get from the abstracts that people had, what were the project ideas that you would want, you're working on, trying to integrate it together. And there were some that they didn't have a unifying theme, and so others did. And so what I want to try and do is get a chance to be tying what we're covering into things that are of interest to you, like getting a chance to see that some of you guys are into robotics. That's kind of cool. A variety of things that if there wasn't a theme that was clearly spelled out, I was trying to just capture some of the points that I was seeing. And so detectors, a alarm clock that came up a couple of times, a wearable fitness tracker, a lot of different ideas, real-time campus activity statistics. And so let's begin to think about some of these. Some of these are a little bit more hardware centric. Some of these are more software centric, but there is still an aggregation of both of those coming together. And I wanted to keep that in mind and have some time that we can be thinking about that together as a class. Let me go over to the Mars MIPS emulator, and I'll spend a little bit of time on this. And I'll ask if there's any volunteers for folks that want to share their digital logic design. And then I wanted to begin to have a multi-part discussion about our projects as we go. So this is a simple program where what it does is it reads in a couple of strings, and then it's going to do an addition and report that result. And so let's just start to break that down at one at a time. So I think I've checked, has everybody been able to get their Mars MIP up and running? I actually would recommend that you have it up and running right now. And so maybe that's what I'd ask. If you have it up and running now, why don't you just give me a reaction so I have an idea? Because I want to verify that you guys are able to do this, and let's have fun together, and let's see if you are able to track what we've got. So this is a key feature that's embedded in this program. So if you just click on help and click on help again, you're going to get this information. And so this is a handy dandy way of getting all of the commands, all the directives, all the system calls and things that are utilized in this program. And so let's look at these directives. And so we just go to the directive tabs. And so here is the dot text. So this is subsequent items, instructions stored in text segment at next available address. And so here is what you have to put in before you start to do your code, your lines of code. There's the dot global. And so this is declare the listed labels as global to enable referencing from other files. And so here we're having main. And so very common in Java or whatever to have your main method be the significant part of what you're doing with your coding. We could have loops now, and we can have this go to main. That would be something that we could do. So we see those types of directives. And then we have this first command, and this is, I did this a couple of times ago when I was looking in this list and it wasn't here. It's getting a little bit frustrated, and actually what it is, it's in this next one, extended instruction, which they call sudo. And so we'll get a chance to be thinking a little bit more about that. And so here we have this load immediate. And so that's what it means. And so we're doing this load immediate of 4 into $V0. And so $V0 is right here. So we want to print string syscall code number 4. And so what is a syscall? So 4 is printing a string. So we're trying to inform the system that we want to be printing a string. And it's message 1. So we go down here, what's message 1? So this is another directive down here. Dot data. So subsequent items stored in data segment at the next available address. And then we have these are reported as ASCII, ASCII Z. Store the string in the data segment and add a null terminator. So there's a distinction between ASCII and ASCII Z. So enter A, enter B, enter, and then it says A plus B equals. And then we have a new line. So these are the 4 ASCII things that we have set up here. And there's some blank spaces here that are included. So let's look at this a little bit at a time. And now when we start to get this explanation, I think that you'll be able to practice either. You notice that there's a lot of comments. And so for assembly language, these names are what they are. And so they're not exactly user-friendly at time. And you can also see that this is another thing that in this integrated development environment, you print something in or you start to put part of a naming convention that can give you a heads up of what it is. So we print the message 1. So enter A. Then we do the same thing as we did here. I'm sorry, first thing is we get the input from user and save. So we're reading registers and putting them in different places. And so here it's implied that there's a keyboard or a console that you're entering this information in. The CPU doesn't see that. We're real close to the CPU. And so what the CPU sees is registers. And so we have to be doing this IO calls of getting information back and forth with this. And so first you print a string to the console, then it wants to receive that. So it has a syscall that we're setting up, number 5. So number five is to read an integer. So we're seeing that be laid out here. So we're reading an integer. And then it takes that information, the syscall results is returned in $V0. We'll see that. So that's message, and then we have message, should we do the same thing? So these lines of code are repeated, and then we do an add. So let's look up the add, basic instructions. So we have add, we have actually a couple different types of adds here. And we're going to be adding 2 integers. So this is addition with overflow. And so we'll get a chance to see what that's like. We add those together. We do a syscall. The first thing we do is we have this nice way of saying it's going to be showing this A plus B equals. And so we're writing to the console again. So that's syscall code number 4. And then we want to print the sum. So we're going to be doing a syscall of 1. So we're going to be syscall 1. Is we're going to be printing an integer. So we're adding 2 integers together and printing it out. And here is the integer we have that stored in a memory. And so the integer for print must be loaded into the register $A0. Then we print the string. And then we print the new line. And then we have a clean exit, which is a syscall 10. So are people's tracking with what I did? I tried to go through that slowly and show you how the helper files can guide you in this process. Any questions on that? Okay, any thumbs up, at least on for some. Glad you're following with that.
I have a question.
Okay, Nathan.
So are these just like simple commands that we could just find on the help tool that's like given to us? Like are these just all just like simple commands we put in and
Yeah,
um
yeah, this is the kind of examples of what I would want to have you guys get familiar with assembly language programming. And you could be, so like the first one was, I showed you was a hello world. Maybe that would be like this first one is you're just writing a string. A second one is you add two registers. A third one could be something more complicated. But this just gives you an idea of just trying to give you an exposure. And this is why I wanted to have folks have a project idea, is trying to relate this to something that you're interested in. And so a calculator, well, actually what we did here, we had a very simple calculator, an adding calculator. So this would be an example of something that could be for that. Several folks did something related to home security. And so this would be what you're thinking about as a register is a way of capturing information. The way that the CPU sees it, inputs from a sensor that goes through input and output is now into the realm of how a CPU deals with those information. And this gives you an idea of what that would look like.
Can we run that piece of code right there, that sample
Yeah,
code?
yeah, sure. So let's do that. Remember which button. I think this is the right one. Okay, thank you for asking for that. So what we can see now is this actually expands this some more, and I'll run it in a second, but we can be seeing there's different ways of how I can be reporting information. So this is for this area here. I can either have it just defaults in decimal. I can put it into ASCII. And that's a way of trying to distinguish between just having it in decimal is just having that slash. I can be putting it into hex. And so 0x in front of it is a way of having x. And this just changes the address portion to either a hexadecimal number. And so those are just two possible ways that we could be reporting that information. So first we have this li command. And so this is actually showing you what it's going to be looking like in hexadecimal. Let me just double check that. Is this hexadecimal? Yeah, this is in hexadecimal. So let's go back to that table I showed earlier just for a minute. So here are the hexadecimal bits that we have available, 0 through F. And so for this emulator, they don't have them shown as capital, but here we can see like this is a small c. And that just gives you an idea of that. So this is actually what's coded into the computer. So we have this level, this is the high level assembly language, this is compiled. And so there's more things that are laid out here, a few other steps that are included. And so let's just go ahead and run this. And so I'm going to do this in single step mode so we can just get a little bit more sense of what's going on with this. So the first thing It does a syscall. I'm going to write something to the console. Look at one more time. So that's the message that's going to be loaded and printed out to the console. And then this is, whenever you see a syscall, that's when it's actually going to be executed. And so it's enter A. That's the first thing that is done. Okay, a couple people were asking how you type into Mars. Let me show that in a minute, okay? And so we enter A, and so see doing it like this is okay. Now it's ready for me to put in something. So I'll put 2, return, and it's going to take that information and it's going to put it into a register T0. It's going to do the same thing for the next message, enter B. Just have to go single step through a few more steps. It's going to do the syscall for that. Now it's asking for another number. I'll put in 3. Now we see 3 is loaded into another register. Okay. Now we're going to be writing to, we're going to take those values and we're going to add them together. And that result is put into T0. Okay, now we're having another syscall. It's going to print something to the console, so A plus B. And then it's going to move the result to the right address so it can then print it out. Do a syscall, it prints out 5. Then it's going to have a new line, so it's going to go to the next line. And then it's going to do a clean exit by doing syscall, the right syscall to do that. And then we have that program finished. Okay. So people tracking what we've got there.
Yes, thank you.
Just to clarify, so the LI is just storing the result in the what do you call
LI
it?
is the load immediate. So you're loading for an integer into V0. That's what that means, LI. So the first tab you want to look at would be the basic instructions for LI. You're going to find that it doesn't show up here. They have LUI, but for the extended pseudo instructions, this just gets into the guts of how things are emulated. These are some additional commands that are here, okay? And various possibilities, polymorphic ways of how you can be including information and what it's going to do with it.
So I'm getting a little confused here. So like, why do we use like why don't we like have a print string that's set to like 4? Like why are we using LI, I guess?
Well, this is an example of it. You have to ratchet things down a layer or two of what is going on here. And so an arithmetic logic unit or something, it's a very low part things that you're doing. And so one at a time, you're breaking what we would be used to that you could do in one single higher level language step or command. It actually requires multiple steps at this level. So you want to be thinking like, what do you want to be doing? If you want to be printing to the console, this is what you have to do. You have to use syscall 4. And so first you want to be, say, okay, I want to do print something in the console, and you have to have something that you're going to be, actually you want to be doing. And then so to write something in the console, it actually takes 3 commands. And when you see the compiled, actually, it may actually take more than that. So there's actually 4 lines of code that are shown here. So you don't need to necessarily worry about that. So this li is decomposed into an add IU and LUI. So this is why it's a pseudo command. And so you can do that, but it's actually the compiler actually breaks it down into a couple. I'm going to answer a question from some other folks here. So some folks are having a problem trying to write something into this. And so let's see if I can create a new one. So it could be a permission issue that some of you are having. So like that first, something similar to what I already wrote, an li $, v0, comma 1. That's your first line of code that you have. And so let's see, did that work? Was it, a couple of you folks were trying to, Freddie, did you get that to work? Were you able to do what I just did, those steps, and get it to work in your environment? Okay, good. Just wanted to make sure. And you can see that once you get the rhythm of assembly language, it just, to do something, it's a lot, there's more sub steps that you're getting a chance to have to explore as you do it. And so this is kind of the sense of what's going on. And when we do some work with our Arduino kits, we'll see a little bit of this kind of a characteristic, and maybe that will be helpful for you. Well, I'm glad that folks are putting in some comments here and continuing to participate with my polling. But let me check and see if everyone has been able to track what I did. Okay, so what I would recommend between now and say next Thursday, get this working. Try and see if you could put in some lines of code here. And let's start to get you engaged in a productive way, thinking about your second sub project. Okay. I'll just go back to this item, and one of the things that I was finding is some people were struggling with coming up with an overall project idea. And so I understand that. And maybe as part of our discussion, I'm hoping that more and more people will feel comfortable to start talking about what they're working on and what they're learning and what they've observed from each one of these things. And so I'll just take at random a few things that I'm seeing here, but we're going to be coming back to this again and again. So the one that we did would been one of the types of things that we would be doing for a calculator. And so we briefly got some introduction of the the elements that come together to form function, you can do an add in digital logic. We'll get a chance to be seeing that a little bit more. And I think I may have one of those that I could pull up here either today or next Thursday. Here there's a couple of folks that have a timer and so or a clock, and so thus you need something you can think like a every computer has to have some kind of a clock, but then with that increment, you could then thinking about, well, let's turn that into a wall clock that's able to tell the time from midnight to the end of the day, or a timer that you could start it and do a countdown or a count up. One other student was looking at a wearable fitness tracker. And so let's start to think about, well, how does each one of these projects actually help you to be conceiving of a project like this? And let me see if anybody has any comments or questions about that they'd like to share about. And if not, we'll come back to this on Tuesday, and I'd like to get a chance for folks to give me more of your input on this. All right, well, I'm going to come back to that. And one of the reasons why I put out an announcement that I really want to have people joining us in class on Tuesday in person and Thursday with us together as a group is I want to make sure if the different ways I'm trying to share the information, if it's getting through, or maybe I need to be doing something different and getting some perspective, and then having some conversations that we can gradually build on as we work through the course. So how many of you have been exposed to binary? Anybody before this class, have you had to be thinking about binary numbers? I know we have folks that are engineers, we have other folks that are computer science, and so we have two large groups in that regard. Okay, at least I'm getting a chance to see more reactions, and so that's good. Anybody ever heard the term hexadecimal before? Is that something that you guys have been exposed to? Okay, so these are concepts that we're now getting a chance to get some insight into, and we're trying to be thinking more of how a computer thinks, and that's been something that could be a little bit new for us. So like here is a top level computer, and we're now going to this layer at this point. And so we're programming this. And so we're having to load information into the registers. We're having to tell the arithmetic logic unit what it's supposed to do. Is it supposed to do add? Is it supposed to do subtract? Is it supposed to do a load? Is it supposed to be doing a store? And there's control that needs to be passed on, like we had like this load immediate, for example. Well, what is immediate? And so all of those has to be defined, and ultimately what all of that has to be put in terms is ones and zeros. And so we come back to this table again, that this is a level that now we're getting exposed to. Probably the closest we're going to be getting to all of that is with this emulator. And so here we have a fairly robust program that we have here. And I just was starting to just give some people a little bit of hope that you can be writing in a few lines of code and begin to create something of your own. So any comments or questions on what I talked about in terms of the number systems. Okay, does anyone want to share their digital logic design? Otherwise, I can start to just go around the virtual room and begin to have a chance for you all to be sharing.
I could share one, or I could share mine.
Okay, let me stop sharing my screen.
Just give me a sec. I gotta pull it up. Uh, do you want me to show all of my designs, like all three?
Yeah,
Okay.
well, one of the reasons why I want you to do that, Nathan, is showing the progression, the relatedness. And so this is one of the things that I want people to get some insight into what we have.
All right. Let me share right now. Are you guys able to see my screen?
Yeah, great. You zoomed it in really well.
Okay. Okay. So, for this project I'm doing, for the theme of my project I'm doing is like building sensormatic systems. Basically, using sensors in a way like that will detect motion or for heat signatures, but for now I'm just gonna work on just motion. Um, So basically, I'm using the sensors on doors. So if you were to walk to a door, there would be a sensor that will detect you and will indicate like, okay, there's someone that wants to go to the door, so the door will open. So, uh, so if I were to play this simulation right now, so this indicates that like all the doors are closed. If there's no light on, or no, wait, yeah, if there's no light on, that means, yeah, if there's no light on, the doors are actually open. Um, and with these LEDs that are not on, that means that just the system's not on. So if I were to turn one on, okay, that's one door is closed. If I turn on the garage door and then the kitchen door, then the system will actually turn on because I want to have these two doors to first connect to an AND system on its own to indicate that those systems are on, that system's on, and then connect to the final AND gate, which will then become the final result of to the system that will indicate, okay, all doors are closed. So now the system will turn off, or system will turn on. Um, so that's just like the basic idea of like how I want my project to go, with just the doors that need to be closed in order for the system to work, or in order for like the sensors to work. Um, and then like if someone were to like come to the door and want like, the door wants to be open, the sensor will detect the person coming, and then the door will close and the system will turn off. So for the second design,
Yeah, before you go there, Nathan,
yeah.
um, so one observation I can be making about what you've got here, and you notice that the garage door and the kitchen door are connected to one AND gate. And so let's say, for example, your garage door, you have that, and your kitchen door is a way that you go from your garage into your house. And
Mm,
so this would be a way that you could be, it actually has the utility of having that first gate. It gives you an incremental way of looking at a part of your overall design that you programmed in digital logic. So if you were just like to click on the garage door and the kitchen door, because you had that as a partial step here, you would see that you get one of the LEDs turns on. And so that's actually that could be a useful feature, and so you can have multiple things that are coming out of a design. That's just one of the points I just wanted to make, but you can keep going.
all right. Okay, and then I'll show my second design. Sorry, I had this screen sharing thing's like in my way, so it's hard for me to. Okay, so this is my second project. This is where I started to add more to this first design. Uh, so I guess what I've added was just more inputs, or I guess like windows, if sensors were onto windows. So basically it's kind of like the same design as like I did with the first door, or the first design. Where first I want like the doors to be checked in like with their own AND gates, and then resulting to the final AND gate to detect that the system will go online. So let me turn it on. So if I were so turning it on, oh, actually another thing I added to this was like an LED light, and I kind of wanted to use it in a way that will show that like if one of the doors or windows are open.
Mhm.
So let me press these two doors. So this is going to indicate, okay, these two doors are closed. So its own AND gate system will turn on, and then reflected this light that like, okay, there still needs to be windows that need to be closed. So I turn on or I close the windows. So I turn on the inputs, and then the resulting AND gate will result in true that like, okay, the windows and the doors are closed. Um, and then the AND gate results will then result to the final AND gate, and then notice that this light bulb's not on anymore because all the power is now going directed to this final AND gate, or
Mhm.
just detecting that like all the doors are closed. And then once the AND gate gets the final result, like resulting in true that the door and the windows are closed, then the whole system will turn on.
Yeah, looks good, Nathan. So I'm hoping everyone has seen how this is sort of a adding on to what Nathan had already had. So it has a developmental nature. This is something you can do. Other folks were talking, they would just have three different sub designs for each other. If that's what you like, that's also something that would be acceptable.
Okay, and then on to my third and last one. So third design, I a little bit more to it. And I think what helped the most was like, because what I wanted to do for this one was, instead of adding like having just doors and windows, what if I wanted to implement like devices around the house that we use, like stuff in the kitchen, like, or stuff that we use like AC or the stove. So I wanted to kind of add that kind of stuff, like if to help indicate that like the AC and stove's on, then we need to turn it off. Um, so I was actually able to find like another LED light that would be able to connect to both the three gates.
Hmm.
And the reason I used a NOR gate was uh, because I wanted to result in a what was it? Because these two are false if they're not on. So this just results in true. So I wanted to remain true to the NOR gate that both these devices are not on.
Hmm.
But if I were to go ahead and turn this on, so I have the doors open just like in the second design. But what actually changes is that when I close these doors, the LED light will go on, and the result will go to the final AND gate. Or no, actually, no, it'll go to this AND gate first. Because what I wanted to do is I want to have this NOR gate actually connect to the final AND gate system. That with these two AND gates connected to this AND gate and then to the final AND gate. So I close the windows too, so that indicating like both of these results are true, that the doors are closed, and the system will turn on. But as soon as I turn on this device to indicate that this is on, the LED switch will actually turn on,
Hmm.
because there's no power like going into the final AND gate anymore, because one of the like either the AC or the stove is on. Um, so uh, yeah, I think that's it.
Yeah, well, thank you, Nathan. But before you leave this, I want to make an observation or two for folks that may not be familiar with them. So folks that are engineers may have a little bit more insight into this. But if you notice about in the middle of the chart, like where you have the AND gate, the front door and the garage door and the output, there's a little round circle on the wire. If you see that, it's above that three input LED, and then keep going up and a little bit further, and then a little bit more to the right. No, not up, to the right, right there. You see
Okay.
there's a little bubble there. What that indicates is that those wires are connected. Now, if Nathan was just to go down a little bit further, um, right above the LED, but below the one that had that, you can see if there's not a red if there's not a bubble like that, it means that they're not connected. And so if you see, if Nathan just goes a little bit right there, that's another connection. So you can see that's one of the ways that you get into this conundrum, how you have wires all over the place. And some you want connection and some you don't. And it can get kind of difficult to figure out how to make things wired together and not have it be confusing. So this is one of the ways that you can do that. So that's something that, especially for the computer science folks that may not be familiar to you, you don't have to have something this complicated, but this gives you a nice way of how you see a design. It works, then you add to it. It's a great coding practice. It's a great design practice. You go to those levels of a working prototype and you build a little bit more on it. Everybody follow with what I just conveyed? Okay. Thank you very much, Nathan. Appreciate you sharing your project.
No problem.
We're getting close to the end of our time, but let me see if there's anyone else that wants to be sharing a project. Otherwise, we can save it until next week, and I'll be dedicating some more time for folks to get a chance and to do that. Okay, so remember, I really want to be spending time with you all. And my goal is not to have it be a dry lecture. At times there is some technical material, but I also want to make sure that you're catching it and also put it in different ways that you can get the concepts and start to actually use it. And doing some of the project work is where I'm trying to bridge the gap between those as best I can. Okay? So the Lord bless you guys. I hope you have a wonderful rest of your day, and I'll look forward to seeing you all next Tuesday. Bye-bye now.
Thank you.
Professor, I have a quick question, if you don't mind.
What's up, Nathan?
No, I don't even remember.
I don't have too much time, Nathan, because I have a class right after this. So
Okay. Oh, it was about